right? That tells you if you have a bridgehead in your product, what that tells you is that you added a, sorry about that, something cyclic and something acyclic, right? So it can be either or. It can be your dienophile is cyclic and your diene is acyclic, or vice versa. And by acyclic, you know, I mean, what I mean by that is not cyclic, right?
Mm-hmm.
Okay. So something cyclic plus something acyclic, that's normally you'll get what's called a bridge between those two. And that bridgehead, it's not always going to be oxygen either. Sometimes it can be another atom. Actually, let's do another example, and then maybe it'll clear up. Let's see. Erase this. We'll do the forward example. So what if I had something like this with no atom there? What would the product of that look like? Oh, that's kind of sloppy.
The same thing. It'll be cis.
Yeah, so it'll be a similar type system, right? You'll have a 6-member ring. Is that right?
Mm-hmm.
This is 1, 2, 3, 4. 1, 2, 3, and 4. And then between 1 and 4, obviously there's a carbon there, a bridge. Following?
Yep.
And then if this is 5 and 6, this is 5 and 6 over here, right? So the point I'm always going to go back to is that if it's a 4 plus 2, the major backbone is going to be a 6-member ring, and then those two methyl groups are on the same side of that double bond. So I'm going to make them cis on this side also. The 4 plus 2 cyclo addition is really like the fastest way to make a 6-member ring. If you're trying to make a 6-member ring somewhere in a molecule, that's the easiest way to do it, is to do a 4 plus 2. All right. And any other questions about that?
Mm-mm.
Shouldn't it be a double bond on 2 and 3?
Say that one more time.
Shouldn't it be a double bond?
Oh yeah. Thank you. Between 2 and 3. Yeah, you're right. There's a lag between my iPad and my laptop for some reason, but at least it's showing up. But yeah, you're right. That's my fault there. There should be a double bond between 2 and 3.
Dr. Russell,
Yes.
the bridge will be angled towards whichever molecule is the ring in the reactants.
Well, that's kind of I don't want to say that because that's kind of a general statement. But the reason I drew it like this, like the way I have it shown, is just for continuity, right? Because on this side, that's the way it's pointed, right? So it's really, the structure is really not flat. It's really a 3D structure. And so that's why the bridge is actually pointed up. And so I want to generalize it by saying it's got to go one way or the other. The easiest way to do it, in my opinion, draw in the 6-member ring first, and then put the bridge in by between the carbons where that bridge shows up. So right here, it just so happened to show up between carbons 1 and carbon 4, right? But I don't want to put you in a box like that, because the bridge is actually, I'm gonna make some room down here and I'll show you. It's actually a 3D structure. So it actually looks like this, right? Where this is the bridge pointed up. And then this
How would you know where the bridge came from without it? Like, how would you know which reactant it was that was cyclic without that?
Well, that's really not consequential, right? If you look at the product, if we work backwards, we can put the arrows in here and then here, and then here, and go back to those star materials. So it doesn't matter which one it came from. It's not, it doesn't like change the outcome of the reaction, if that makes sense.
Okie dokie. Thank you.
No problem. Now, if you were to start with, I think I kind of understand where you're going with that question. Though, if you started with something like this, right, where the double bond was here plus this, yeah, even that wouldn't even give you the same thing just because of the location of the double bond. Yeah, so I really don't think that's a it's a good question, but it's not going to affect like the outcome of the reaction. If you're able to, if you know which bonds to break, then when you get to the star material, you'll be able to see where the bridge came from anyway. But that's really important to understand that when you have a bridge like that, that you don't touch those bonds. Now, if you do that, then you're straight. Does that kind of, I know I didn't answer the question directly, but I hope that gave you a little bit of clarity.
Yeah, that helped.
Okay. All right, let's go down to some examples. Hopefully you all have printed this handout by now. Hold up now. Let's see. Okay, yeah. Let's do a few examples. Do I want to do that? Yeah, let's do this one. It's a lot going on, but we can work through it. So it says deals all the reaction of a monosubstituted diene, that's this, with one substituent. And a monosubstituted dienophyl like this, it says gave a mixture of two products, but the 1,2 disubstituted product, that's this one, predominates. It says draw the resonance hybrid for each reactant and then use the charge distribution to explain why the 1,2 disubstituted product is the major product. All right, so this is it's asking a lot, but it's really not asking a lot, right? So let's break it piece by piece. So first it asks us to draw the resonance hybrid for each one. So let's start with this one, right? But you do see the product, right? The 6-membered ring here in both cases. So it's definitely a 4+2. Let's draw the resonance for this star material. Let me see if I can get some. Yeah, I got room right there. I just need to zoom in. So that looks like this, right? Anybody remember what that CHO, what that is? And it's an abbreviation for a functional group. Anybody remember? No? All right. No dead space. Less editing. All right. It's an aldehyde. Anytime you see CHO written like this, it's an aldehyde. It's just an abbreviation for the aldehyde functional group. All right. Now here's the question. What would the resonance form for that look like?
The double bond for the oxygen would make it the electron.
Would it look like this?
Oxygen, yeah.
And this?
Mm-hmm.
Is that right? So the resonance form would look like this. And then this carbon right here, it's a CH2. It's going to be positive. Yes or no?
Mm-hmm.
Yeah.
Let me fix that oxygen up there. So the oxygen is going to be negative. and then the carbon is going to be positive. Is that right?
Yes.
All right. So let me ask you a question. If you were to attack this compound with a nucleophile, where would you attack first?
Would it be at the CH2?
At the car.
At the carbon, right? You know that if you draw the resonance form, that carbon is positive, yes?
Mm-hmm.
All right. And so now let's look at this molecule because it's going to be a little bit different, right? Because now you have the OCH3 group on the end. Is that a donor or is that an acceptor? Anybody remember the difference between a donor and an acceptor?
It's a donor.
It's a donor. It's got a long pairs of electrons that it can donate. Are you following?
Mm-hmm.
So if I draw the resonance form for this, right, it's going to look like this. I used those, my bad. That's positive, and then that's going to have a lone pair, and that's going to be negative. Yes or no?
Yeah.
All right. So when we take those two and put them together, I'm going to draw it out so that this is cis. Right. What's going to happen here? Actually, I should have let me draw it how the product is because I don't want to make it more confusing.